All right, so let's get to the main material in the lecture. So I start the course with a discussion of return calculations. And so the primary thing that we're going to look at in terms of financial data are asset returns over time. And so it's worthwhile to spend a bit of time to define what we mean by asset returns. And so that's the subject of this topic. And for many of you, again, a lot of this is material that you would see in a financial economics course in the beginning of a finance course, talk about present value calculations, the time value of money, and so on. So we'll start with the time value of money, and we'll start with the notion of future value. So we'll say we have an investment, we have V dollars today, so we have $100 today, we're going to invest it for N years, and we're going to get a simple rate of interest R per year. Okay? And so again, think of this: deposit your money in a money market account. The money market account pays an interest rate 1% per year. How much will your money be worth after 5 years? And so that's a typical future value computation. And interest is assumed to compound once per year. So the interest rate would be an annual interest rate, and the bank is going to pay you interest each year. And you want to know how much will your money be worth at the end of N years. So future value, so how much money you have at the end, is equal to how much you start with times 1 plus the interest rate raised to the power N. So that's the standard future value computation. In these kinds of problems, I like to draw a timeline that gives you what's happening to your money at different points in time. So you can have time 0, time 1, time 2, up to time N. We start with V dollars today. And so what happens after 1 year? So V dollars grows to V dollars. So you keep your $100, and then the bank pays you an interest rate of R%. So after 1 year, your initial investment grows to your initial investment plus the initial investment times the interest rate. So that's the interest that you earn. So this is the future value after one time period. So what happens after 2 time periods? Now we have an initial investment of V times 1 plus R. This grows to an amount after 2 years. You're going to get V times 1 plus R times 1 plus R. So that's what you started with, and then you get your principal plus your interest. And so that gives you your V times 1 plus R squared. So after 2 years, this is your future value. And then you just continue on that same compounding. And after N years, you get your future value, which is your initial investment, and then your 1 plus the interest rate raised to the power N. Okay? So that's future value. So as a practical example, say if you start with $1,000 in a checking account, pay a simple annual interest rate of 3%. By today's standards, this is high, right? So right now, banks are paying at best, 1% per year, which is historically extremely low. So what is your future value after 1, 5, and 10 years? So after 1 year, you get $30 in interest. After 5 years, then you get an additional $159. And after 10 years, you get an additional $343. So again, this is the power of compounding. As your money grows, the payment of interest on interest, leads to this sort of exponential increase in your wealth. Now, this future value function that we wrote, so this future value function, future value is equal to initial value 1 plus interest rate raised to the power N. This is an expression that contains 1, 2, 3, 4 different variables, right? And so given my initial investment, given the interest rate, given the number of compounding periods, I can figure out what my future value is. The same thing, if I tell you what the future value is, I tell you what my initial investment is, I tell you what the compounding periods, I can solve for what the interest rate is on that investment. So taking our future value formula, if we solve for the initial value in terms of future value, the interest rate, and the number of compounding periods, we get present value. So what is the, if I know I get this amount in n years, and I know the interest rate is this percent per year for this many years, this is how much money I started with. So that's present value. So when you think of the timeline, future value is out here. That's money that you receive n years from today. The present value is what is that future value worth today, right? So that's what the present value calculation says. Then you have, we can take the future value formula, this thing here, and we can solve for the interest rate. And so if I tell you, 10 years from now, you're going to get $5,000. You start with $1,000, and it's a 10-year investment. What's the compound annual return on that investment? That's just solving the future value formula for the interest rate. So the interest rate, which is future value divided by present value raised to the power of 1 over n minus 1, that's the average annual interest rate that you get every year that compounds such that your initial investment grows to the future value. And then we can also take this future value formula and solve it for the investment horizon. That is, if I tell you the interest rate, the present value, and the future value, I can solve for n in this relationship. We can think of this as the investment horizon. And so how would you do that? Then we just take the logarithm of both sides of this. Or you take v, future value divided by v. That's 1 plus r to the power n. Take the logarithm, solve for n. And then we can solve for n this way. Okay. So one of the things I want to do with this investment horizon, there's sort of an interesting example. Consider the following question. How long does it take for your money to double? Right? So you have an investment. Start with $100. And you know the interest rate is 3% per year. How long will it take you for your money to double? So we can use this relationship here to solve that question. And this gives rise to a rule of thumb that's often called the rule of 70. So ask the question, how long does it take for your money to double? Okay, so I'm going to take my initial investment V, and so we know that this is equal to, the future value. We want to be 2V is equal to V times 1 plus R raised to the power n. So our initial investment is V, and then we want our future value to be twice our initial investment. So that's doubling our money, right? So notice that when we take a look at this, the V's cancel, and so I can look at this as saying the logarithm of 2 is equal to n times the logarithm of 1 plus r. Okay? And so then I can solve this and say n is equal to the logarithm of 2 divided by the logarithm of 1 plus r. Okay? So this is an expression, an exact expression that tells me how many years it will take for my money to double if the interest rate is equal to R% per year. Okay? Now, the logarithm of 2 is approximately 0.7. And one of the things we'll see from calculus, if you do a first-order Taylor series approximation of the logarithmic function, if the rate of return is close to 0, so if it's like 1% or 2%, then the logarithm of 1 plus r is approximately equal to r. So we can approximate this exact result by 0.7 divided by r. And so this gives the rule of thumb that's called the rule of 70. So for example, if the interest rate is 0.01, then n is equal to 0.7 divided by 0.01, which is 70. So if the interest rate is 1%, it takes 70 years for your money to double at compounding at 1% per year. So all this money you're putting in your savings accounts right now is getting paid 1%. It'll take 70 years for that money to double. So again, that's just an illustration of working in computational finance. You have a formula. You do some simple computations to get a result. All right. Now, very often in investment situations, compounding of interest can happen more than once per year. So if compounding happens m times per year, for example, m could be 2, so you can have semi-annual compounding, or you could have monthly compounding, so that's m would be 12 times per year. You can have daily compounding, so m is 365. So if you have compounding m times per year, what's your future value formula? Well, what you do is you take your annual interest rate, you divide it by the number of compounding periods. This becomes what's called the periodic interest rate. So if m is 2, this would be your semi-annual rate. If m is 12, that would be your monthly rate. And then your future value is your initial investment times 1 plus the periodic rate raised to the power m times n. So this is the number of years, the number of compounding periods per year. Okay. Now, we have something called continuous compounding. So think if we're going from compounding from daily to hourly to minutely to every second to every millisecond. So as m essentially goes to infinity, so we're compounding instantaneously, then we can take the limit of this as m goes to infinity, and it turns out that this is equal to v times e to the rn. So continuous compounding involves the exponential function, and e to the 1 is 2.7. So what does compounding give us? So here's an example. Say we have an annual interest rate of 10%. We start with $1,000, and then we look at the future value after 1 year with different amounts of compounding. So if you compound annually, you get 10% interest, so you get an extra $100. If you compound 4 times per year, then you're going to get an extra $3.81. Okay, so that's what the 4 times compounding gives you. If you compound weekly, you get an extra $5. If you compound daily, you don't get a whole much more than what you get from compounding weekly. And if you compound continuously, it's effectively what you get if you compound daily. Okay? So increasing your compounding frequency leads you to get slightly higher interest. I mean, for historical reasons, this notion of paying interest more often than once a year was one way that banks can get around certain kinds of regulations that capped interest rates. So there used to be regulations for savings and loans that said they can only pay interest rates of 5% per year. But the regulation didn't specify how often you can compound. So if you can have an annual interest rate of 5%, but if you compound continuously, you effectively offer a higher interest rate. So that's an example of getting around a regulation by being a bit clever. Now, because we have compounding periods that could be different from a year, there's a concept known as the effective annual rate. So we saw that when we compounded, say, daily, we got $105.16 of interest, right? And when we compounded once per year, we only got $100 of interest. So effectively, we have a higher annualized interest rate when we compound daily than when we just compound once per year. The effective annual rate is what is the annual interest rate that gives us this future value. Okay? And so our effective interest rate is essentially 10.5% instead of 10%. So how do we solve this? So to calculate the annual rate that gives you the same future value with compounding m times per year to compounding with 1 time per year, you solve this equation. So here, our initial investment, our periodic rate, this gives us our future value with compounding m per year. This is future value compounding once per year at this interest rate, which would be the effective annual rate. And then we take this equation and we want to solve for RA. So just do some simple manipulations. We get that the effective annual interest rate is equal to 1 plus the periodic rate raised to the power m minus 1. Okay? And so we can see in our example, and then similarly, if we have continuous compounding, do the same computation. We have, this is the future value with continuous compounding. This is the future value with compounding once per year. And then now we want to solve for the effective annual interest rate. That's going to be e to the interest rate minus 1. So let's do some comparisons or computations. Suppose we have a situation where we look at a effective annual rate with semi-annual compounding. Okay, so we have an investment with a simple annual interest rate of 10%, but interest gets compounded twice per year. What's the effective annual rate on that investment? So you solve 1 plus the annual rate is equal to 1 plus the semi-annual rate squared. Solve for the annualized rate. You get 1 plus, this would be 5% squared minus 1. And so our effective annual rate is, in fact, 10.25%. So it's effectively higher than just getting simple interest. Okay. So if we do a comparison, compounding once per year, 10% interest, compounding quarterly, we get an extra 0.38%. Weekly, you get an extra 0.5%. And then go to continuously an extra 0.52%. So you can see, effectively we get slightly higher interest when we compound more often. So this is one of the reasons why when you take out a credit card, they don't charge you an annual interest rate. Well, they quote you an annual interest rate, but they compound interest daily. So your effective interest rate is higher than the annual rate that they quote you on your credit card. And how much higher is it? You do this calculation.